Thank you. I like to move.
Yes, everything is fine. Thank you.
Thank you.
Thanks, Natasha. Great. Let's get started. So it's a pleasure to have Raquel Queiroz from Colombia. Raquel did her PhD at Max Planck in Stuttgart before moving on to a postdoc at Weizmann, and then ultimately landing in Colombia, where she's done all kinds of really exciting things, trying to demystify how the geometry of bands influences physics in correlated electron systems, and she's going to tell us about some of that work today. Thanks.
Thank you, Hart, so much. Thank you, everyone. It's great to be here. Thank you. All right, so I want to tell you about quantum geometry today, and basically I tell it in this way, how to picture bound electrons in periodic lattices, in the sense that basically I want to make this connection between how to talk about bonding, chemical bonding in a lattice, and what's the correct language to describe this, and that's the words that this has what quantum geometry is going to bring us that, and that might be like a kind of unfamiliar concept, but I'll try to make that a little bit clearer in this talk. And please do interrupt with any questions at any time, and I'll be happy to answer. Okay, so let me start with this not working. Let me start with this not working again.
If you click on the screen, it's a Zoom thing. So if you click on the screen, you should be able to get the
Aha, good, perfect. Okay, so let me start with this. What makes these two materials different?
the electric cost.
Correct. Exactly. Okay, my talk is done. Okay, very good. But clearly this one is made shinier, is strong. Salt does have a much smaller refractive index. It is brittle, and basically the difference between these two materials. One could just start by answering, okay, like how am I going to see the difference between these two? The first thing that I would do is a band structure calculation, and I would look at the band structure of these two as a condensed matter theorist, and I would see that they basically both insulators with very large gap insulators. Okay, this is taken from some database, so the DFT, the gap is slightly underestimated and so on. But the point is that they have both around 5 eV electron volts of band gap. And which means that you should expect it to behave relatively similar, but they don't behave like that at all. So the differences in the physical properties between these two materials are not encoded in the energy, just the band dispersions of these materials, but rather in something else. And what that something else can only be the wave functions. Okay? And if I were to look at just charge localization, and this is of course a schematic view of this. Here is the lattice structure of diamond and rock salt. They both have 2 atoms in the unit cell, so the unequivalent atoms in the unit cell. This is a diamond lattice. This is salt lattice, where basically your electrons are localized in your negative ions. And here the electrons are localized on the bonds, but they still, if you look at charge localization, actually that has to do with the spectral gap of your system, and they're both very localized in both cases. And on top of that, these are crystals, and because they are crystals, they have translation symmetry. And if you're going to look at the wave functions of both of these cases, these are completely extended wave functions, Bloch states, which span the entire crystal. But there's a very obvious difference between these two. If you were a chemist, like he was saying, what is she even talking about? This guy is a covalent insulator, and this guy is an ionic insulator. What does this mean? Is that the electrons in the covalent case, they are shared between adjacent atoms. Well, in this case, they are not. So if I were hypothetically to track down the quantum motion of one electron, I would see here the electron to jump between a much larger volume than in this case, in the ionic case. So the question that So this is this definition of bonding, this different type of bonding between these two materials. I want to understand how does it affect the physical properties and how this is actually, how can I define this based on response theory. Okay. So how do I talk about the sizes of orbitals in just not in a lattice, but not just in an isolated atom? You can ask myself, what is the size of an orbital, of an s orbital in this case? Well, this is simply given by the fact that the Hamiltonian, in this case just the harmonic, like the hydrogen atom, does not commute with position operator, right? So there's an intrinsic uncertainty in the position of an atom, which is given, which I can compute, basically computing all the dipole transitions between different energy levels of the hydrogen atom. So if I imagine, so here this is the dipole operator, just a position operator, and it will because it doesn't commute to the Hamiltonian, it necessarily will bridge this gap. And I can basically see that if I had my gap between energy levels to be extremely large, right, these dipole transitions will be harder to perform. And then I would expect to have my orbitals more and more compact. And of course, more compact, it also means that they are a bit more geoid. So I can find basically an uncertainty of the position operator is something that would go like 1 over the energy gap. This is in atomic orbitals. So this is, what does this mean? That the fact that I have this uncertainty in position can be thought about, it's like as a response function. So if I have, what does this mean? If I have some kind of force, which I can apply by putting an electric field in my system, how easy it is to create a dipole moment, right? So there's no dipole moments in any of these s orbitals or p orbital, and in order for me to create a dipole moment by applying a force, and I can calculate like how easy this is to do by how easy it is to mix these orbitals, because when I mix this orbital, then I can have an individual dipole moment. And this susceptibility to the polarization is going to be the dielectric constant precisely. So that's nothing but the refractive index, and you can see how the different materials are going to behave very different from like how they are going to, interact with the light. And in fact, there's some, there's a lot of body of work from the 60s and 70s relating precisely the dielectric response to the type of bonding. But this, I feel like it was a little bit set in that point because DFT kind of took over. So many of now there's like this enormous black box where we can just compute everything directly. We can compute this dielectric response directly, and we don't think too much what are like the minimal ingredients that make this dielectric response larger or smaller. So why?
Each in freshman course that this is volume of the atom. Flexibility is volume of atom.
So this in this case, this is just Bohr radius, right? So the question is precisely what is Bohr radius squared, right, in the lattice? Now when we have an infinite lattice, and that can be an issue. And why is there an issue? The issue is that defining polarization or really defining the position of an atom in an infinite lattice or something with periodic boundary conditions there's some intrinsic problem with it. And this is not really, so if you were to just naively calculate the polarization based on the charge density, like you would do for a molecule, you would have a problem. Because, for example, so you are integrating this over a unit cell. And now if you have a repeating pattern of positive charge and negative charge, then you can see that if I choose this repeating unit cell, and I will calculate the net polarization, I will just charge the distribution with respect to the center of the positive charge, that will give me 0. So there's the basically 0 bulk polarization. And if I were to just choose a different unit cell, I would get a different number. I can get a and that comes because of the system it has periodic boundary conditions. And that's an issue, and that's an issue that was resolved by King, Smith, and Vanderbilt in 1993, where basically what they said is that it's fundamentally impossible. It's really something, the polarization, the bulk polarization of solids is not related to the charge density. It's in fact related to some geometric quantities of the phases of the wave functions. So this is basically the solution. The solution is, instead of calculating the polarization this way, you're going to promote, instead of thinking about position, you take the derivative with respect to momentum, but now, of course, momentum is not a good quantum number in the crystal, so you take the derivative with respect to crystal momentum instead, and instead of looking here at the density operator, you look at the projector into your ground state. And when you do that, so this is here just a example, like an example of a band structure. So you have momentum, you have energy levels, and you have bands which are formed. And what you can do in order to calculate the bulk polarization, which it's going to be, if you are going to choose a different basis to represent your field states, instead of block states, you would construct localized states which are orthogonal. They are called Wagner functions, where these Wagner functions would be centered. That is a gauge invariant quantity, and you can calculate that quantity, so the expectation value of the position operator, by calculating these periphases. So the expectation value of the position operator, and here is the derivative with respect to momentum. Okay, so now I talked about polarization, and I was telling you about sizes of these orbitals. How can you possibly define the sizes of these orbitals in a lattice, in an infinite lattice? So we should be looking not at the first moment of the position operator, but second moment of the position operator. That tells you the variance in the position when you evaluate it with respect to your ground state. So if let's just look at this operator here, P is the projector into your field states. 1 minus P is the projector into your empty states. And here you have sandwich RR. So you can see naively that will be just R squared minus expectation value of R squared. So that's the variance of position operator. But this is actually tricky. This is not an equality here, because if you have topological invariance and other things, there will be, if you compute this quantity, you would get infinite, and if you compute this quantity, it's not infinite. So this is the correct way of actually computing this quantity. But you see something nice, which is here you have position operator, and here you have projector into your field states. So imagine that your states, your ground state was perfectly localized, right? It was a position eigenstate. If that's the case, then these guys will just commute, right? And then P times 1 minus P is exactly 0. So you can see that this is quantifying how far you are of your ground state is from a set of position eigenstates. So this is a tensor. We call this guy the quantum geometric tensor, which really just, in a sense, what it does. So here, if you think about, this is your field states and this is your empty states, what this operator basically is measuring is the rate of virtual transitions induced by dipole transitions, right? So PRQ here, it will be the probability of jumping over there, given a position, and then coming back. So this is quantifying like the rate of dipole transitions, virtual dipole transitions that you have, which is basically, making your states fat in your ground state. So there's two parts to this. There's a quantum metric part and a very curvature part, which is nothing but the symmetric part and the anti-symmetric part of this tensor. Now, it's kind of interesting because if you just consider, you can apply the same thing for an atom, right? You can talk about the sizes of the orbitals just basically looking at this operator, but this guy would not exist. This guy is really fundamental, only appears, it's only from the quantum interference of the lattice of infinitely many electrons that you can have orbitals, which are fundamentally new. And they can have something like an antisymmetric component of this dipole fluctuations, which really means that there's some kind of like vorticity to it, okay? Which is going to be something that I will tell you a little bit more about. so this quantum-metric part here is really the size, the longitudinal size of your orbitals. So it's x squared and y squared. And what it measures is the localization of the electrons in the ground state. So you can, this quantity here, since this is, think about, there's two ways of thinking about that. You can think about it as measuring the position, uncertainty in measuring the position. But you can also say that, okay, the position is nothing but a change in momentum. So you can, this actually maps down to the problem of twisting a little bit the boundary conditions of your system, or applying a little bit of a field that changes the momentum, because momentum is just a gauge freedom. So then what this is, this maps down to the problem of that was introduced by Conrad, like how do you distinguish a metal from an insulator? So an insulator is insensitive for you to because your states are completely localized, so they are insensitive for you to twist your boundary conditions, while in a metal they're not. So in a metal, these sizes basically they blow up to infinity, and in an insulator it's a finite value. And this nice connection to geometric quantities, it's mostly done by these two papers by Resta and Sorella in 97 and Sousa Wilkins and Martin, which talk about this in this geometric Now, this quantity here, I computed it all based on the projector, which is your full ground state projector, but you may as well just look at K by K. That will be fine. That will be a quantum geometric tensor now evaluated at each momentum. And once you do the evaluation of this at each momentum, you find out that this is nothing but the Berry curvature, as you probably know, in momentum space. And you see that the symmetric part of this is actually going to be the non-adiabaticity of the state. So if you take two Bloch states, which are close by, and you project one to the other, you can ask how much norm was lost. And that is going to be measured by this quantum metric. So the symmetric part in momentum space, this is telling you that there's some non-adiabaticity when you move in momentum space.
The quantum metric does not have to have the symmetry of the lattice, right? Or symmetry.
I think it will just, by definition, will have the symmetry of the lattice. You know, these guys are local without a function.
G does not diverge in an insulator.
Sorry?
You're looking at an insulator, G does not diverge. Does it still have the symmetry of the lattice?
It will have the symmetry of the lattice. It will have the symmetry of the lattice. There's no reason not to, because the P projector itself, you know, retains all the symmetries of the lattice. And position operator is something completely local.
So the simple question, so G is the dimensionality of G is square of distance, correct?
Yes.
And that distance is size of the wave function. So the square of size of wave function
Yes.
localized.
Yes.
Correct?
Yes. But it's actually okay. Let me continue because that's wave functions in block in crystals. They are infinitely extended, whether you are in an insulator or in a metal. And this is something that's finite in an insulator, right? So it's telling you something a little bit slightly. Yes.
A very stupid question, going back to the previous
Okay.
slide, the very last formula,
Mm-hmm.
UK plus delta K are not symmetric. And still you get linear term canceling out. The rest is quadratic in delta K and dk. Should it be symmetric UK, your K plus dk over 2 and your K minus dk over 2, and then linear term cancels out?
You are saying, why did I take the derivative? I shifted just this one instead of shifting it
Well,
symmetrically.
the way how it's written.
Yeah,
the one
well,
not
I
symmetric.
don't,
So then the question is, what about linear term? Should it be symmetric form and then linear term cancels out?
The linear term of the Perry connection.
Let's be very phase. There should be very phase.
Let's move.
So that's, yeah, so it should be substantive because this is the quadratic term. That's what
Sure,
that's
sure,
what
quadratic,
I
yes,
wanted to
absolutely.
get. Anyway, so the fact that you have this very curvature, and now here I'm putting it in terms of momentum space. It turns out that this guy, if you integrate it over the entire Brillouin zone, can be an integer. okay? And that integer is the Chern number. And it's really kind of like quantifying how much that there is some, so how can you read this? It's the antisymmetric part of position in X, position in Y. So in momentum space, this is nothing but like making a little shift in Kx, Ky, and back. So you are making a little loop in momentum space. That's what you are evaluating by evaluating this very curvature. So you're taking, so if this is non-zero, there's a flux once you do that, right? And if you integrate this flux, that flux needs, because this is a compact space, so this flux needs to be an integer. And it turns out that this is a Chern number. And if that Chern number is non-zero, this tells you that there's some really something non-trivial about how you interchange X and Y, right? So motion in X is related to motion in Y. And it will, of course, so here, this is the Haldane model that implements this in the lattice. This isn't the same as you will have in the floating Pole effect. This will number that will count just how many boundary states you will have in the system. But it's important to notice that if commutation in X and Y is non-trivial, if I have something which is perfectly localized, like supposition eigenstate, X and Y is the same, right? So if I need to have like this non-trivial relationship between X and Y, then I need to have basically a certain size. I'm required to have a certain size. So you can imagine that this size will necessarily be bounded by this number. So you need to have some amount of fluctuations in the X and Y direction in order to accommodate this vorticity. So there's a minimum spread to the orbitals, and you can see basically this is for the Haldane model. I'm tuning here the mass, and I'm going from a topologically trivial phase where the Chern number is 0 to a topological phase where the Chern number is 1. And what is happening is that, let's see here, what's happening is when I am right here, and this mass is very negative, basically, I'm completely localized in one of the sublattices. And as I change the mass and the mass becomes exactly 0, there's actually kind of a frustration of where the electron should be. Yes.
No, in differential geometry, it's not very natural to consider integrals of the metric itself. You normally think about integrals of like the Ricci scalar or something like that. So I was a bit confused by the previous slide. Is it natural here for some reason?
So this guy here, the entire integral of the Brillouin zone of this is this. Because what I did here in this yeah, I just like evaluated this K by K because I can do that if I have translation symmetry. So I broke down this entire quantity into K by K, but what matters as like the size fluctuations, what matters is the entire ground set. You evaluate this in the entire ground set.
Right. I mean, I understand that. I can't stop you from integrating the metric if you want. I'm just saying that, like, if you think of it as a metric, right? That's a notion from geometry. So normally we don't think about integrating the metric itself. We consider integrating derivatives of the metric.
But this is
parameter. The next slide.
Yeah, this is a parameter in the Brillouin zone. So I basically.
I mean, this G average is also G mu.
Yeah. This is us. Yes. This is mu. Oh, there should be a mu on the left.
Yeah.
Okay, so that created confusion. That absolutely should be a mu.
Okay.
Yeah. Sorry for that.
Momentum average.
Momentum average. Yeah, this integrate over the Brillouin.
Thank you.
Sorry for that. Okay, that was it. Thank you. Okay, very good. So basically, what happens here is when you are very negative mass, your electrons are very bound to one of the sublattices. And as you're now tuning this mass in this parameter and you're going to go entering in the topological phase, you get into a point where your electrons must delocalize over the entire lattice, right? Become a metal. In fact, this is a Dirac metal. And then when you go in the topological phase, you recombine everybody. And once you recombine them, you have them delocalized over some amount of space in the lattice and getting some this vorticity into it. Because that's just a visual picture of seeing this relation. Yeah.
Sorry, just a quick, so in the picture that you drew, it looks like changing the sign of the mass is like flipping the red and blue subclasses. So it's like, from that point of view, it's a little confusing as to understand, why that leads to a phase, to topologically distinct phases.
Yes, because I have another mass here, which is T2 in this case, where this is aldane. I have an aldane mass as well, so here I'm plotting two curves.
Okay.
And it's,
Okay.
look at the black curve, and in the black curve is actually selecting one of these. Okay, so if it was zero, there was no Haldane mass and there was no flux, this would be completely symmetric, and that would just be graphing, basically gapping graphing with positive mass and negative mass, and you can see it's actually completely symmetric, right? The sizes. But if you put the Haldane mass now, you favor one, and you go into the topological phase.
And you're saying the Haldane mass is associated with this hackle.
Yes. Yeah. So that actually determines, this term determines the chirality. Otherwise, it wouldn't be a way to determine this chirality. Okay, but the point is now you have your electrons, you can think about them as going around in graphing. This is a model for graphing with a flux. They go around, on these plaquettes, and they have a chirality to it, right? And the thing is, how do I now understand this orbital, which this orbital cannot exist really on its own as a normal orbital? How can I understand this orbital, this local object, and basically what I'm proposing is let's look at response functions. Just look at how it responds, as an insulator. So the natural way of understanding how the geometric quantities is by looking at basically instantaneous response, really like short time response of the system. So the proper, so that would pick up the local properties of your orbital. So the way that we did this is basically looking at Kubo formula, and because Kubo formula is the current correlation function. Now current is nothing but the time derivative of position, right? So here time derivative. So let me just go slowly here. So this is current. This is the time derivative of position. So here, what you basically grading this with the energy differences, right? Because time is just 1 over the energy. So time derivative here gets this energy component, and here R M N are just the matrix elements of the position operator, and omega n is just the energy differences. So when I write this in this way, which is basically choose a basis and make a lemon representation of the Kubo formula, you can see that this current correlator basically contains two positions. Okay, so this you have here position and a position. Now, of course, you will have more response if you're driving the system with a field that is resonant with a frequency resonant to certain transition, right? So this is what you're seeing here. So if you look at the response at frequency omega, you will have a response if there's a transition. There's two states separated by that energy. But you can see here that there's position squared. So there's position squared. Let me rewrite this in terms of geometry, because why not, right? This is something we can do. So this is, I'm going to just look at this and write this down as the quantum geometric tensor, or the matrix elements of the dipole correlation function. So if I were to write exactly in the same basis here, the quantum geometric tensor, which is just this quantity here, P stands for field state. So I have here Fermi function telling you that these are field states. Q is empty states. So I have here 1 minus Fm, and I have position matrix elements. So here, this is nothing but the quantum geometric tensor. I can compare these two. But I want to take the comparison a little bit further. And in order to do that, I need to involve energy. So the response knows about the energies, right? It knows about the Hamiltonian. And while here, the quantum geometric tensor only really knows about the wave functions themselves. It doesn't know about the energies. So let me fix that, and fix that by noticing that the quantum geometric tensor is nothing but the dipole correlation function at equal time, right? But what if I just do time, dipole correlation function at different time? Then I'm going to pick up something about the energy. So if I look at position at time t and the position at different time t prime, then how am I going to introduce this time is just by time evolving these operators, which picks up a phase of E omega m and t, right? And this is now a time-dependent quantum geometric tensor, which is just a dipole-dipole correlation function at different time. What is nice about this? What's nice about this is that this guy just tells you the spread, right? Like this tells you the spread of the states at a time t, and conductivity is nothing but the rate of spread of the position, right? So then I can just rewrite conductivity in terms of this quantity, which is nothing. This is a response function. This is a correlation function, right? So I need to here have some causality. That's the theta that appears there, and I have the time derivative. Now this picks up only in the antisymmetric part of this correlation function. And that's important because this correlation function is not an Hermitian operator. They have an Hermitian and an anti-Hermitian part. And they will actually correspond to different types of response functions. So you pick up the antisymmetric part, and that antisymmetric part will actually contain both metric, because they are at different time. I took out this slide actually, I should have left it here maybe. But because it has if you're looking at non-zero time, if you just take the antisymmetric part of Q, it will contain both the metric and the very curvature with a cosine and a sine here. Okay. So this is what you get, which is kind of like a nice visualization of what this dipole correlation function should be. And once you look, for example, at low frequency response, so if you have an insulator, so this actually works also for metal, which is nice, and I'll show you a little bit more about it. But if you look at low frequency response, which means that you don't have a Fermi surface, you have a gap, and everything that you have, the dynamics of your system will be purely coming from dipole-dipole transition. But everything is geometric in a sense, okay? And once you do basically an expansion of this, you can see very nicely that what you get, this is here is Fn minus Fm, that comes from taking the antisymmetric part. And then you have the metric matrix elements, or the symmetric matrix elements of the dipole-dipole correlation function, plus I, the antisymmetric matrix elements of the dipole-dipole fluctuations, times 1 over omega m. You can expand all of this to small frequencies, and you can see quite neatly what happens here. So at 0th order, so DC conductivity, which must, again, there's no Fermi surface, so there's no charges to go around. So if you have DC conductivity, it needs to come from edge nodes, right? It needs to be something like that. So you can see very neatly that this appears here. If this is 1 here, this guy is antisymmetric. This is Fn minus Fn. So you must pick up total very curvature. So you get here is Tk and n. You get the peaks E squared over h times the Chern number, which is this number here. But if you start going to higher order in frequency, you also get more and more geometric contributions, which are no longer just the antisymmetric part. So DC response is only going to know about Chern number. But if you just go to AC response, right, then you now are divided by omega mn. That is antisymmetric because that's energy m minus energy n, right? So now this is antisymmetric. You must pick up this is an n. So that they must pick up the symmetric part. Okay, so you see that in AC response, the non-dissipative AC response of the material must be metric matrix elements or symmetric matrix elements of the dipole fluctuations divided by the energies. Okay, so the first term here is nothing but the quantum Hall effect, the E squared over h times c, the Tk and n invariant, and to the first order, what you get basically is the polarizability of your system, or the electric constant that's going to come out of here. So this is I squared over omega times this quantity, and this quantity is nothing but convoluting the metric matrix elements divided by the energy gaps. Now this is it's going to be bounded. Of course, this can be many numbers, right? This is going to be bounded by the average metric. The mu nu is still there. Sorry, I didn't put it. The mu nu is still there. Divided by the spectral gap. And this will determine basically the dielectric constant of the insulators.
So this is
Yeah.
capacitance of non-interacting electrons.
Yes, there's no interactions here. It's so yeah.
If you go back one slide. So if I set omega to 0, I
Yes.
take on the leading term.
Yeah.
So what happens with this real part?
Drops out.
And
This
the
is
reason
you're multiplying with Fn minus Fm here. So this is symmetric and symmetric as well. Yeah. Okay, so this will define the dielectric constant of insulators. And once you just go about comparing this number with, you just take out of the energy gap, which are two things that you have available for you in experiments, and you just start comparing things, you find you can make an estimate. Now you need to be a little bit careful on how you make this estimate because this quantity here is a length squared. So you need to, and then you take the integral. You need to take an integral with respect to just 2D over the momentum space in order to get something that is dimensionless. Anyway, you do those things in a proper way, and you find out that materials generally cluster. Okay, so there's some ionic insulators tend to have larger gaps, but also smaller sizes. Covalent insulators somewhere in the middle. Topological insulators have smaller sizes and even larger. But this, if you go and compare it with the actual metric that you would get out of, say, a tight binding Hamiltonian, and you would calculate this, you see that it's kind of off. So you do better by, instead of taking the minimum possible value here, you take the maximum, you take the typical optical transition. So you go and you look at the optical conductivity, you see where's the peak of the absorption, then you take that instead, it's called the Penn gap. And now you can actually see that you get a metric which is always within 10% of the real thing if you would calculate with the FT. So the atomic insulators, they're really quite small. They have really tight orbitals, and the covalent insulators, they must have like larger orbitals to basically accommodate getting to the other atom, right? And in topological insulators, they are much larger. You know, they're substantially larger orbitals than you would expect even for any kind of like trivial topological insulator, trivial insulator. And in fact, you can make an estimate of what the size would be with respect to the gap. And it's not very obvious, so how to make this, but because the metric itself depends on the gap, and then there's also, anyway. So, but you can make an estimate of what this size would be, and it's something that goes log of delta, and you can see very nicely that materials tend to fall in that line, unless there's something that it's forcing your orbitals to be bigger. And what is something that is forcing your orbitals to be bigger is usually some topological invariant like the Chern number. So all the topological invariants are substantially larger orbitals than you would expect just based on the gap. Yes.
Sorry, I thought that the tensor only knows about the wave functions and not the gap. So how do you get some delta dependence in G that enables you to get to the log?
So that's the thing. This is the magnitude. So if you just think about how the gap is created, right? So you have a band folding, and then you need to gap. And when you gap out, then you create a bunch of optical transitions. So the matrix elements of position operator are big when the gap is small. So that's
in the figures that you started with, there are many gaps in insulators. So when you say log delta, is the minimum gap or?
So no, this is the typical gap. I'm basically, it will become clear in a couple of slides. But the point that I want to emphasize here is that every time there's some kind of like topological obstruction, meaning there's some reason why you cannot completely localize, then these orbitals tend to be big. And this is the case for like topological insulators, or even in the case of just normal covalent insulators like silicon or diamond. What happens here is that you have two sites in the unit cell, which are exactly equivalent. So coming back to diamond versus salt, salt had two inequivalent sides, so the electrons could go compactly to one side. But if you have diamond, they're exactly the same, and electrons don't know where to go. So even if you, so they are shared. So even if the gap is very, very large, which happens because carbon is very, very light, electrons will still need to be completely delocalized over those two sites. Okay, that's why you would, for the same, about the same gap, you have a substantially larger value of the metric.
But it's not, that's too much volume. Where is it?
So so this is in terms of metric, but what it ends up being is that the refractive index has about a factor of 2, and that makes a huge difference. So this is a question of numbers when it comes to yeah.
So the indices on G are suppressed in many places. So are all these statements supposed to be true for all components of G, or are they some?
No. You need to basically, this is a 2-dimensional quantity, so you need to make an average in the Z direction. And in many materials, this is isotropic and you can do it. In other materials, it will be different, right? If you look at the spread this way. But also the dielectric response is non-isotropic generically in materials when there's no when the different QVC. Yeah.
So you're also saying that for those topological materials, permittivity is anomalously large,
Yes.
owing to the Dirac.
Yes, exactly, because there's a topological invariance, even if the Dirac curvature is exactly 0, which happens in all of these topological insulators where you have time reversal symmetry and inversion symmetry. This dielectric constant is absurdly large for what you would expect from the same one. So if you want to make a mirror or something, or you need to start engineering these things. So
Really all you need is just edge modes then, time reversal symmetry presumably doesn't actually matter.
no, the edge modes are not that important. So if you have the topological crystalline insulator without, it's not about the edge mode.
I see.
It's really about the quantum fluctuations of the position. They're big if you have a topological. So these orbitals are big. So there's a I'll try to get to it. Okay. Anyway, so so another thing that we noticed that it was nice to write this in terms of a dipole-dipole correlation function at different times is that if we think about the size or the vorticity of these orbitals, we can also think about other things like the magnetic moment or the effective mass. Okay, so these are all different properties or instantaneous properties of the orbitals themselves. And they can be captured very nicely. Instantaneous orbitals means that it's a small time. So it means that you integrate all frequencies. So you can recover those quantities as sum rules. Okay. It turns out that all the sum rules, which are basically given by how much dissipation you will have, you know, that you can have, because you can dissipate if your dipole moment is along the field, or if you have magnetic moment across, you know, so you can have whole type of dissipation, or you have longitudinal type of dissipation. You can have both. And so this guy, if you integrate the dissipation over different powers of omega, then what you're actually getting is the different time derivatives at this point. Okay, so you basically what this is telling you is what are the 0 point motion fluctuations of your electrons locally. And this will have a size that will be the 0th derivative in the vorticity, but you can also look, instead of r squared, you can look at r dot v or r cross v, which will be the orbital angular momentum, and this will just be different derivatives of this. Okay, so this guy will come out. So you can, and then what is nice about this is that it's such a simple formulation that you can compute that, you know, as long as you know projector into your ground state, and you can make some nice approximations about this tensor, about understanding what is important for it. So yeah.
So first of all, can eta be fractional or eta is always integer?
I only look at integers. I don't know what eta means for more than 3 numbers. But so I know that 0, but I can show you the ones I know, but the non-integers, I don't know what they mean. But
Yeah,
they mean something. I don't know what they mean.
And second question.
Yeah.
About this. So we have this nice sum rules. If experimentalists come to you and say, we want to measure something. So what comes out from this formula? Okay.
Okay, so eta equals to 0. Okay, so if I integrate the longitudinal conductivity and divide it by omega, I get G. I get the size. So that's called the Sousa-Wilkins-Martin sum rule. Now, this is hard because you have to have access to the entire energy spectrum. And in fact, I think that it's hard for a reason. It's fundamentally hard. So we have a paper, which I kind of took out the slide here, but where we map this problem to, instead of being the linear response, you look at a step response where you suddenly turn off the electric field. You would do the same because the field gets all the 1 over omega. You can pick up that thing, but it has the same type of problem. There's always a problem here, which is you need to know about the entire spectrum. You always need to know. It's not a ground state property in a sense. And I think that's a fundamental aspect of this G, of this size. So that's something to keep in mind. The imaginary part of here, this is just Kramer's chronic of the Chern number. So you get basically pk and n back. Okay, so that's the 0. So that's the sizes. That's r dot r and r cross r. You can also look at -1, which is what I told you before. That is going to be in longitudinal. That's going to be the polarizability or the electric constant or any other name as the electron susceptibility. Right? That's just basically going to be the spring constant on how easy it is to polarize your electrons longitudinally. This guy, the whole part tells you it's related to circular dichroism. So how easy it is to absorb light, to make a torsion in your system in one way versus the other. So in the one, it's basically in the longitudinal part, that's the F-sum rule. So that tells you basically the charge stiffness of the system. So you basically have N over M. And it has, if you don't have a Fermi surface, you're in an insulator, you just have a contribution to this, which is basically summing like the weight of all of the oscillators. That's going to give you your optical mass, right? But if you have a Fermi surface, you'll also have a contribution from the Fermi surface, and they add up. And if you look at the imaginary part of the Hall, that's the magnetic moment. So all these different quantities, they come out basically of different moments, different time derivatives of this 0-point motion. Yeah.
As you know very well, some of the sum rules are great because you take a directing system, and at the end of the day, you get the result that like for free fermions.
Yes.
Is all this analysis so far for free fermions, and so you cannot extend it.
I think there's nothing. So definitely, there's nice some rules in the sense that they're related to some conserved quantities, right? But there's nothing fundamentally wrong about applying this to. What do I need in order to apply this? Is a projector into field states, a projector into an empty state, and I know to know how my position operator looks like. Okay, so I don't need to have free fermions for any of these things. So as long as I know this, which is hard, because this will know about all the states. This guy is great. This guy only knows about the ground state. He's the only one. Everybody else knows about all of the empty states. So you really need to care about that. And then there's how much you care that also comes out. But there's something, there's a nice feature into this, which is for every eta, there's one that appears as a non-dissipative response and one that doesn't. Because think about Kramer's chronic. If you do Kramer's chronic here, you get the Chern number. But if you were to do Kramer's chronic there, you would integrate from -infinity to infinity, you would get 0. So there's a zigzag structure here, where the metric does not appear as a ground state property or as like a non-dissipative response by itself without weighing by some energy prefactors. The same happens to distortion or the orbital magnetic moment. And so that is kind of an interesting feature.
So are all these things measurable?
Oh yeah, that is a very good question. I think that is
Example, small c, which is capacitance. Is it measurable?
this guy. No, this is measurable. These guys are measurable. These guys are measurable without
C
any
is
trouble.
capacitance, right?
Hmm?
Small c is capacitance.
Okay, so yeah, so you're I wrote test capacitance, read it as dielectric constant or electric susceptibility. Read it as chi e. It's chi e. It's chi e. This formally is chi e. Is the
What would you offer, 3D?
It doesn't matter. it's capacitance for a specific dimension, but like chi is for, it works for all. Okay, so let's keep it chi. So how do we understand this in the simplest case for a Landau level? Because Landau level is nothing but an harmonic oscillator. Okay, so that's all there is. There's only one frequency that matters, which is the cyclotron frequency. Okay, so basically you can see immediately that just p squared E is equal to p squared of 2m, that the uncertainty in position is going to be something like 1 over m times E0. You can see that 1 over m, or the F-sum rule, should be something like G times omega C.
That's called
Right.
magnetic length, X squared.
That's correct. So G here is magnetic length. Okay? So
Square-
no, I'm saying,
square of
so
magnetic length.
that's, so all of the differences, so if I look at metric, they all kind of like, it's the minimal system where you basically have the metric, the symmetric and the antisymmetric part coinciding, the charge stiffness, so the Drude, sorry, I shouldn't say Drude. So the optical mass and the orbital magnetization are the same as basically C times omega C. This permittivity is also C divided by omega C. So it's just powers of omega C that you put in, right? Depending on the different moments. And why do we care? So that we know that this is just LB squared, like you said, Boris, but why do we care? Because it's now, we can generalize it very neatly to something that you have a dispersion. And now your localized orbitals are just something in the labs, right? Some that we need to, that we want to quantify what they mean, which would mean that there's just not one single frequency that is participating in this. There's more frequencies. So you can see that they follow each other. So here, this is for the Haldane model. When we read this this black line, you have topological trivial, 0 Chern number, then 1 Chern number, then 0 Chern number. And then if you look at the different moments, they basically follow graded by, convoluted by some energy. So you can look at distortion, which is going to be, this guy's actually changes sign as you go through a topological transition. You have the orbital magnetization that follows, so you actually can see that you are already starting getting some of this, the just R cross V, you're already starting getting an orbital magnetic moment. As you are approaching the phase transition, and even from the trivial side, you're already starting to twist. And on the longitudinal part, you see that this is the metric, is the black line. You blow up at the phase transition and it becomes larger if you are inside of the topological phase. But then if you're going to look at the mass, for example, which is this color, orange, you can see that if you are in the trivial phase, electrons behave more heavy than when you are in the topological case. So the topological case is quantum fluctuations make you kind of go faster or behave a little bit heavier because you kind of can move and jump. You know, they have like some little quantum jumps that help you on the way. That's a way to understand it.
The
Yeah.
transition there's this, for the optical conductivity, like universal number, which is like 16 squared over H or something that you get for Dirac's.
Yeah, but that's just for one Dirac.
Yeah, you
There's-
count, it's that
Yeah,
times
yeah,
the
yeah.
number.
So that's actually interesting because the Dirac will have a contribution. So if I look at, Dirac will have a contribution for DC conductivity at 0 frequency, but also as you take the limit.
Yeah, the
So
order of
it's-
limits
it's-
matters. So
yes,
I'm
it's
talking
a-
about the optical case where you get a finite number. For
You gotta
DC,
find that
it's-
number, you gotta find a finite number on this case, but that is for the integral of, like, that's for the optical conductivity itself.
Yeah.
Okay, so that will, for G, so divided by omega, that means that there will be bigger, right? Okay, so let me just look at the F-sum rule. And compare you something here, which is kind of nice. So if you have a metal, so the spread, so the conductivity, which has to do with the spread of charge, will contain a geometric part that is oscillating, but it will also contain a Drude part, which is just telling you that, that because you're metal, your charge goes, but because you have these optical transitions, your charge goes with kind of like that, it kind of jumps around. So it has this oscillation. So if you are in an insulator, you don't have that. All your mass is optical. and you just have something that oscillates, and you'll have a peak in the optical conductivity. That information will tell you about the sizes of these orbitals. But if you are in a single band metal, that guy goes away. You just have N over M, and that's the effective mass of the metal, and you just have something that it has just a Drude peak. There's some width here, which is set by the scattering time. But in general, and I think this is kind of important, is that you have both things happening, right? So you have a peak, a Drude peak, but you have some peak in the optical conductivity. So this is where geometry is coming from. So there's telling you something about how electrons go and how electrons are localized. And you can make this, you can separate it in a formal way, right? Should I say something about this? Maybe this, sir?
Sorry,
Yeah.
but that's story about electrons being itinerant and localized.
Yeah.
Normally the story was interaction localized electrons. There's no interaction in your picture.
Not yet, no. No,
So how we should understand the story about mid-infrared peak and through the peak simultaneously?
Okay, so I think this is what twisted bilayer graphene and these things bring you to make us rethink things a little bit more. Which when these scales are very separable and very clear. Okay, so and what happens when you consider interactions? I don't know how far I'm with time, but when you consider interactions,
Technically, you have 3 minutes, but we.
Oh, Jesus. So is that they start, it's a question of time scales as well, right? So should you look at interactions are a little bit more instantaneous? Do they start noticing the localized electrons first versus the itinerant parts? And I don't know if you saw, there's some beautiful data from Shahalalani with this quantum twisted microscope, where you can basically look at the Hubbard gap in the flat bands of twisted bilayer graphene as a function of K. And you can see so neatly that the part which is more localized is really gapping out, and the other part which is very, itinerant is not gapping out. So these are form factors of the interaction that enter. But so the question is how important are those? And so I'm gonna skip that, but basically you can see how this geometry appears. It appears because of lattice interference. You basically always renormalize your orbitals due to lattice interference. So if here I'm looking at square lattice, and I'm gonna kill some of these links. So in the square lattice, I just have a single band Hamiltonian. I have half filling and I have a used through the peak. And now I'm gonna start killing off these links. And what's happening is that I start creating all these optical transitions, and eventually all of this spectral weight becomes at finite energy. What this means is that I've created a flat band, infinite mass, right? But now everything is localized, and now everything is geometric. So that's how you create the shape. You created a localized orbital, but now it has a shape because it basically lives around this plaquette, and that is basically defined here in this part. So this matters for all kinds of things. It matters for moire materials a lot. This is the types of systems that we are now all very excited about, because these bands are so flat that most of the dynamic, everything is basically set by the geometric part. That's why it's kind of a nice system to look at. So things are very localized, but you see that these orbitals, even though they are very localized, they're slightly delocalized. That's the important part. They're not completely localized. They cannot be completely localized. So they're always kind of like covalently. You have, frustrated Lebesgue lattices and some other things, but let me go to this, which is precisely the point that I was trying to make a moment ago, answering Andre, which is now here what I'm doing is a simulation where I'm just putting 3 electrons in potential, which is basically hexagonal lattice graphene. Okay, so I'm binding these electrons to their sites, and what I start having is bands. Okay, now you can see, and I'm putting the chemical potential here. You can see that conductivity will have contributions from all kinds of things. It will have contributions from the Fermi surface that will tell you about the effective mass. That's gonna be the Drude peak. You will have some contributions from dipole transitions between these two bands. Now, it's interesting because if you think about an atom, dipole transitions only exist, that they find the sizes of the orbitals, they only exist between s to p orbital, right? But what can you do with lattice frustration, with making an hexagonal lattice? Is now that you have optical transitions between the same type of orbital, because you create this delocalized bonding. So this delocalized bonding, which is this geometric part, appears here, and the energy that is setting this is this bandwidth, right? Now, you would have also something which is atomic that really corresponds to the dipole transitions between this type of orbitals to that type of orbitals. And if I make the potential deeper and deeper and deeper, this guy will go away, but this guy will never go away. So if I start moving my sites apart, this geometric part will first have to flush all down to your metal, to your Drude peak before it disappears. So that's really like, it's fundamentally different, right? So when we're trying to make an effective model for something, or tight binding model, so this is similar to DFT, right? Because we're considering free electrons. But if you're making an effective model, you can kind of kick out this guy because you don't care about the instantaneous times where you know that you belong to this p orbital of graphene. You can kick that out, but it's important to keep this. And now when we're talking about quantities like these geometric quantities, which are not only knowing, they don't only know about the ground state, it matters where you make the truncation. So the number that you're going to get for metric, and that's why it's hard to measure this thing, and I think it's maybe impossible fundamentally, is that it matters where you truncate your Hilbert space, you'll get different numbers. Okay, so let me just show you here Kagume's. You know, if you're here in the Van Hoff singularity of a Kagome, you could think, oh, you know, you'll have basically an enormous peak. Okay, so I need to, I need to wrap up. Okay, very good. So this is, sorry. And the point here is that this is very different if you're in the upper Van Hoff singularity or the lower Van Hoff singularity. So let me conclude coming back to bonding. Okay, I kind of want to come back to bonding. Just like give me 1 minute to finish this up. So this size is basically some size that you should compare with the system, with the lattice size of your crystal. And if you have ionic bonding, basically it's when this size is much smaller than the unit cell. When covalent bonding is about. But you have some systems where you have this much larger, when you have like, you're frustratingly like sharing the electrons with multiple sites. Think about benzene, right? Graphene is nothing but an enormous benzene, where your electron does not know where to go and it needs to go to further and further and further away. And this G, this metric is precisely measuring that. And once you break these bonds, you'll have, you know, some either, you know, some dangling states, dangling bonds that will happen, or you would have some fractional, like these guys, because they're shared between many, many, many bonds. When you would cut this guy, you would get a fractional polarity, like extra, like you just get a partial electron there. And this is nothing, this is, you know, you can basically tabulate all your materials based on this. Your trivial insulators, completely ionic. Your covalent insulators are what we call obstructed atomic limits, where you have some quantized pi vary phases. And your topological insulators is precisely these quantities when your electrons are shared between multiple orbitals. And when we cut them, you will have some fractional charge, which leads to topological edge modes. And yeah, that's it. Let me not that means already took too much of your time. Thank you.
Lots of questions, but allow one or two.
Yeah, thanks for the nice talk. So in general, the Kubo formula can be non-local to account for things like Dirac transition, right? Does this type of geometric interpretation also go to that case, or is it only limited to local Dirac transitions?
So you say finite Q.
Yeah.
Right. So I've only looked here at Q is Q equals 0, but you can. You can. You would just have different types of terms. You can make an expansion in Q, and you know the first you would have, if you look at conductivity now as a function of Q, you will have some contribution like Q squared that will know about R squared, like so quantum geometry tensor, and then further and further and further on. Yeah, but I haven't explored it completely. Yeah.
Great.
Continue with tradition of asking ideological questions. When you look, when you talk about Drude part.
Yeah.
This is will be really trivial question. Normally with Drude part, there's a factor tau.
Yeah.
Lifetime. Where does factor come from here?
That's-
Correct. But how it appears in your consideration?
So when you right, so the when you for this Fermi surface contribution, you will have basically delta functions over there, a bunch of delta functions, and if you want to turn that in, you can basically regularize those delta functions with a tau.
So tau is regularization of
So,
the.
yes, that comes from the just from the interband part. Yes. Yeah. Yeah, so that, but that just basically sets in the time. So you know, basically this sets you a time of like where you're bound, and then eventually when do you wait long enough and you're basically semi-classical and you know you have a Fermi surface and you are a metal. But going back to your question of like about interactions, it should include some kind of scale of when are we interacting. So because if you are very instantaneous, then we actually care that we are very localized. And now this for me is really like the most interesting direction to go. You know, it's like how does this existence of this geometric part or existence of flat bands, which is not even the blend that I'm talking about, but just there's a flat band over there. How much does it influence really exotic physics that we do see in Kagome materials, cuprates, and so on, that all have mixing of orbitals. All of these materials have orbital mixing. So we should think about.
Is that either ferritic and cuprates somehow is related to what you are saying?
I hope so. Yeah. This is what I want to pick your brain about.
All right. And then for that final broad question, let's thank Raquel again.
Thank you.